Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the rotating magnetic field. Our objective is to learn how three-phase AC creates a rotating magnetic field. Additionally, we'll define and discuss the term synchronous speed and learn how to calculate it. Finally, we'll learn how phase sequence determines in which direction the magnetic field rotates. Key to the operation of three-phase AC electrical machines, motors, and generators is the establishment of a rotating magnetic field. This cunning principle was largely the product of Nikola Tesla's influence. It's impressive because it's simple, elegant, and extremely effective. The direction of rotation of a three-phase AC motor can be changed by simply swapping any two supplied phases, and the operational speed can be varied by increasing or decreasing the number of magnetic pole pairs in a machine, or by increasing or decreasing the input AC frequency. A power electronics device known as a variable frequency drive or motor drive has largely made physical modification of the motor poles unnecessary and directly varies motor speed by changing frequency. Throughout the course of this lecture, I will assume you are at least familiar with basic electromagnetic interaction. Additionally, I'll assume you have at least a nodding acquaintance with basic electricity and electronics, including three-phase AC circuit analysis. This is to suggest a trainload of baggage precedes this discussion. If you lack these prerequisites, make sure to check out the supporting material available at the Big Bad Tech channel. Having said this, don't worry. I'm going to use some very simple diagrams and make some large sweeping generalizations. Realize this is not a lecture on motor windings, and these diagrams are not meant to be taken as the literal truth. It would be artistically impossible for me to accurately represent the sheer number and proper orientation of windings and poles, so these cave paintings will have to do. Recall that the rotating part of a three-phase AC rotating electrical machine, like a motor or a generator, is called the rotor, and the stationary part is called the stator. The terms you'll find are pretty easy. DC machines use the terms armature and field to describe the rotating and stationary parts. One could use these terms interchangeably and people will understand what you're talking about, but it's generally not considered good form to do so. The rotor will be slightly overshadowed in this lecture by its dance partner, the stator, but for now, realize the rotor is the output shaft, i.e. the business end of a motor, or the input shaft of a generator, and may or may not contain a means of electrical connection to its internal workings. If it sounds like I'm giving myself a lot of wiggle room here, I am, because the four main types of three-phase AC rotating electrical machines, permanent magnet synchronous motors and generators, electrically excited synchronous motors and generators, squirrel cage induction motors and generators, and wound rotor induction motors and generators, are really only distinguishable by the construction of their rotor. The stator for all four machines, for the most part, is essentially the same. This lecture has a lot of bang for the buck. For the price of one entry fee, you get 4 deliverables. Not that I'm charging you anything. Do me a favor and click on an ad every once in a while, or write your comments on the back of a $20 bill and send it to me. For now, we can simplify the rotor as having one or more magnetic pole pairs on it. They may be permanent magnets in the case of permanent magnet synchronous machines. They may be electromagnets in the case of electrically excited synchronous machines. Or they may be electromagnetically induced electromagnets with no electrical connection to the outside world for induction devices like the squirrel cage and wound rotor induction machines. But for now, we don't care how the magnets got there. For the purposes of this lecture, the rotor can be simplified as a magnet with a stick on it, where the stick is the shaft and the magnet is all the stuff stuck to the shaft. The term synchronous speed is the rotational speed of the stator magnetic field in units of revolutions per minute, or RPM. Depending on the type of rotor construction, the rotor may or may not rotate at synchronous speed. Synchronous machines, as the name implies, ordinarily rotate at the synchronous speed of the rotating magnetic field, whereas induction machines ordinarily lag the synchronous speed in motor mode and leap ahead in generator mode. The differential between rotor speed and synchronous speed for induction machines is sometimes called slip and ordinarily expressed as a percentage of synchronous speed. For example, a squirrel cage induction motor rotating at 1,760 RPM, where the synchronous speed is 1,800 RPM, has a slip of 1800 minus 1760 over 1800, or 40 over 1800, where 40 RPM is approximately 2.2% of 1800 RPM. If you are seeking superficial understanding of the rotating magnetic field and just want a quick method of determining synchronous speed, here's a formula often used to calculate it, where synchronous speed is equal to 120 times the frequency of the AC system divided by the number of magnetic poles per phase used to construct the stator field. This formula is correct, but represents a limited understanding of the rotating magnetic field phenomenon. If you want a limited understanding, by all means, use this formula. If you really want to understand how the rotating magnetic field works, stick with me, and I'll show you not only the underlying phenomenon, but also a means of interpreting the most misleading parts of this formula. Key to the correct interpretation of this formula is the relationship of rotational speed in units of RPM to frequency in units of Hertz, and distinguishing between the terms pole, pole pair, and the number of poles or pole pairs per phase. It is for this reason I'm going to crack open this formula ever so slightly and write 120 as 2 times 60. This may seem unnecessary, but trust me, this simple modification is key to understanding the underlying phenomenon of the rotating magnetic field. Let us first discuss the relationship between RPM and Hertz. The only step necessary to find an equivalency between these units is a unit conversion. The unit Hertz, if we recall correctly, is a cycle per second, and is a measure of how many ups and downs, i.e. complete cycles, the AC waveform makes per second. Given this fact, the number of cycles per minute could be solved using a unit conversion, where 1 minute equals 60 seconds. A 60 Hertz waveform would therefore make 3,600 cycles per minute, and a 50 Hertz waveform would make 3,000 cycles per minute. It makes sense. If I increase or decrease the cycles per second, I similarly increase or decrease the cycles per minute. This is where the 60 in our synchronous speed formula is coming from. It's a unit conversion. It's converting between something ordinarily measured in units of seconds, AC frequency, to something ordinarily measured in units of minutes, rotational speed. Let us now distinguish between the term poles, pole pairs, and the number of poles or pole pairs per phase. The stator or stationary part has numerous coils or winding, which when wound in the proper direction and excited by a voltage and resultant moving electrical current create electromagnets. An electromagnet, if you recall from the electromagnetic interaction lecture, always has 2 poles. Note the plural S, a north pole and a south pole. 1, 2. The term pole, used in its singular form, is something that really kind of irks me, because you can't ordinarily create a magnetic monopole, i.e. a north without a south or a south without a north. It's like having yin without yang. One is not all one at the exclusion of the other. Magnetic poles are the same. They always occur in pairs, and only in relation to one another is there a north and south pole pair. This is the term I like to use, pole pair. If you think in this manner, not only are you thinking at a higher philosophical level, you will also have a deeper understanding of how the stator is creating a rotating magnetic field. 2 poles make a single pole pair, just like 2 shoes make a single pair of shoes. That's the purpose of the 2 in our formula. It's taking the number of single poles per phase and converting it to the number of pole pairs per phase. At first glance, this formula might seem counterintuitive because the number of poles or pole pairs is on the bottom. By increasing the number of poles per phase, or as I like to think of it, increasing the number of pole pairs per phase, we decrease the synchronous speed. This goes against an intrinsic more is faster instinct most of us have, but it's true. By increasing the number of poles or pole pairs per phase, the synchronous speed decreases. To explain this phenomenon necessitates some explanation. This warm-up is a simplification only, and I'll return to describe the phenomenon in greater detail using super confusing diagrams in a moment. The easiest way to describe decreasing synchronous speed as a function of increasing pole pairs per phase is to think only of a single phase, then divide the 360-degree arc of a full circle into portions dominated by a pole pair. I know there are 3 phases, but for now, just think of a single phase and realize that the other 2 phases are electrically offset from each other by 120 degrees. Imagine 3 layers of cake identical to each other, but offset by 120 degrees. If we describe the action of the first layer, just imagine the same thing happening in the other layers at the appropriate offset. This cake analogy saves you 3 times the confusion and me 3 times the talking. If there is a single pole pair per phase, it covers all 360 degrees. If a single cycle of an AC waveform takes a pole pair from north to south and back again, it stands to conjecture that at 60 Hz, this would undergo 3,600 changes over a minute. If you want an alternate way of thinking about this, you could also say a 60 Hz waveform takes 1 over 60, or approximately 16.7 milliseconds to complete a single cycle. If you stood there for a full minute, you'd see 3,600 cycle changes. Notice I'm using the term pole pair per phase. If there is a single pole pair per phase, this means there are 2 poles per phase. If this is a 3-phase AC motor, it means there are really 6 poles. If we substitute these figures into our formula, keeping track of what terms we're using, when operated at 60 Hz, we find the synchronous speed for a single pole pair per phase motor to be 3,600 RPM, exactly as we anticipated. This same motor operated at a slower frequency of 50 Hz will rotate at 3,000 RPM, again exactly as we anticipated. If, however, there are 2 pole pairs per phase, each pole pair covers 180 degrees each. Each complete cycle of the AC waveform only brings the rotor halfway around, and that first pole pair simply hands off the rotor to the second pole pair once it's completed its angular portion of the rotation. It makes sense then that this would take twice as long as a single pole pair operated at the same frequency. At 60 Hz, where each cycle of the AC waveform is approximately 16.7 milliseconds long, a complete revolution would therefore take 2 times 16.7 milliseconds, approximately 33.3 milliseconds. If you stood there for a full minute, it would complete 1,800 changes. Again, notice I'm using the term pole pair per phase. If there are 2 pole pairs per phase, this means there are 4 poles per phase. If this is a 3-phase AC motor, it means that there are 12 poles. If we substitute these figures into our formula, keeping track of which terms we're using, when operated at 60 Hz, we find the synchronous speed for a 2-pole pair per phase motor to be 1,800 RPM, exactly as we anticipated. This same motor, when operated at a slower frequency of 50 Hz, will rotate at 1,500 RPM. A 3-pole pair per phase motor is essentially more of the same. In this case, we can say each pole pair covers only 120 degrees each. Each complete cycle of the AC waveform only brings the rotor a third of the way around. The first pole pair hands off the rotor to the second pole pair once it's completed its angular portion of the rotation. The second pole pair then hands off the rotor to the third pole pair once it's completed its angular portion of the rotation, and so on. It makes sense then that this would take 3 times as long as a single pole pair operated at the same frequency. At 60 Hz, where each cycle of the AC waveform is approximately 16.7 milliseconds long, this complete revolution would therefore take 3 times 16.7 milliseconds, or 50 milliseconds. If you stood there for a full minute, you would see 1,200 changes. Again, I must remind you of the terms I'm using. Notice I'm using the term pole pair per phase. If there are 3 pole pairs per phase, This means there are 6 poles per phase. If this is a 3-phase AC motor, it means there are 18 poles. If we substitute these figures into our formula, keeping track of which terms we're using, when operated at 60 Hz, we would find that the synchronous speed for a 3-pole pair per phase motor to be 1,200 RPM, exactly as we anticipated. This same motor operated at a slower frequency of 50 Hz would rotate at 1,000 RPM. Can you see the pattern that's forming? Every time a phase adds another pole pair, the base rotation of the stator magnetic field is divided by the number of pole pairs. At 60 Hz, the base rotational speed of the stator magnetic field is 3,600 RPM. A single pole pair per phase stator magnetic field rotates at 3,600 divided by 1, or 3,600 RPM. A 2-pole pair per phase stator magnetic field rotates at 3,600 divided by 2, or 1,800 RPM. A 3-pole pair per phase stator magnetic field rotates at 3,600 divided by 3, or 1,200 RPM. Without going into all the flim-flam and hand-waving I did previously, I'm reasonably confident you can understand that a 4-pole pair per phase stator magnetic field rotates at 3,600 divided by 4, or 900 RPM, and that a 5-pole pair per phase stator magnetic field rotates at 3,600 divided by 5, or 720 RPM, and so on. If you wanted to do this same analysis for motors operated at 50 Hz, you'd find the following figures. It makes sense. Increasing the number of pole pairs per phase decreases the synchronous speeds. If one always operates at a fixed 60 or 50 Hz, there are only certain quantum levels of synchronous speed that one can attain. This is essentially how a separate winding multi-speed motor works. By selectively connecting or disconnecting pole pairs in a stator, one can vary the synchronous speed of the motor between 2 or more predetermined levels. If you want the motor to spin fast, connect less pole pairs per phase. If you want to decrease speed, connect more pole pairs per phase. Such large quantum jumps between predetermined speeds, however, aren't exactly the smoothest means of speed control. It is for this reason that multi-speed motors have largely become a thing of the past and are being replaced by motor drives that keep the number of pole pairs fixed and increase or decrease the supplied frequency. Consider a motor drive operating a 4-pole or 2-pole pair per phase motor, not at 60 Hz, but rather 57 Hz. Our formula suggests the stator magnetic field would revolve at 1,710 RPM. If the motor drive increased the supplied frequency to 63 Hz, our formula suggests the stator magnetic field will revolve at 1,890 RPM. This is very neat. This method requires no physical modification in motor connections, and simply by varying supplied frequency, one can fine-tune the rotational speed of the stator magnetic field. Before we move on to the confusing details that follow, let me remind you that this discussion of pole pairs is not just applicable to motors. The rotational speed of the generator input shaft used to supply an AC output with a desired frequency is dependent upon the number of pole pairs in the generator stator windings. Generator shafts can be directly driven or can be driven by a step-up gearbox intermediary. Consider a modern horizontal axis wind turbine that necessitates the generator be driven at 1,910 RPM. This rotational speed slightly leads the 1,800 RPM stator magnetic field produced by a 2-pole pair per phase, 3-phase AC stator excited by 60 Hz AC. This represents a slip of approximately 6.1%, and this slip is essential to both asynchronous and doubly fed induction generation. We'll discuss these methods in later lectures. If a step-up gearbox with a 1:83 ratio was used, the rotor, being the combination of the hub and 3 blades, could spin at a relatively lazy but high torque 23 RPM to drive the generator at this speed. That's the purpose of the gearbox, It trades torque for speed. If this turbine had to directly spin at 1,910 RPMs, imagine a 77-meter diameter bird Cuisinart exploding the eardrums and hearts of everyone in a 10-mile radius. Wind turbines already have an undeserved reputation as creations of Satan himself, and directly driving a 2-pole pair per phase generator at this speed is not a recommended practice. Consider, however, a 100 pole pair per phase permanent magnet synchronous generator with no gearbox intermediary. In this case, if the rotor is driven at a relatively lazy 25 RPM, it would output 3-phase AC at approximately 41.6 Hz. Power electronics intermediaries can rectify this 3-phase wild AC output into pure DC and then invert it to grid-compliant AC with a proper phase sequence, magnitude, frequency, and phase shift. There are advantages and disadvantages to both approaches. Gearboxes might be costly to maintain in remote offshore environments. However, direct drive generators, because of the sheer number of poles that must be incorporated, have very large diameters and are exceedingly massive and costly. All these costs and benefits need to be considered as technology advances. Lest you think direct drive generators be confined to the most modern of wind turbines, look no further than your local hydroelectric plant. Consider Powerhouse 1 on the Oregon side of the Bonneville Dam in the Columbia River power system. This powerhouse features direct drive synchronous turbines with 96 poles or 48 pole pairs. These generators can rotate at a relatively slow rate of 75 RPM to produce the desired 60 Hz AC. Powerhouse 2 on the Washington side features a couple generators with more poles, 104 to be exact, or 52 pole pairs, to produce the desired 60 Hz AC output at a slightly slower input speed of 69.2 RPM. If you've ever been inside this facility, you'll immediately realize how incredibly large a direct drive turbine has to be, especially one designed to produce 43 to 66 megawatts of power. Now let's move beyond our earlier simplification and see how 3 phases interact with each other. Again, this is not meant to be a lecture on motor windings. Even these dirty details are at best cartoonish simplifications. Let's start by examining a 3-phase AC single pole pair per phase stator. One could also say that this is a 2-pole per phase stator, or since it's designed to run on 3-phase AC, a 6-pole stator. The stator necessitates 3 windings, A, B, and C, one for each phase. Pole pairs are created from the opposite ends of a single winding wound around an iron core. We'll call the opposite ends of each winding A and A prime, B and B prime, and C and C prime. These windings could be electrically connected in a wire delta configuration, but the electrical configuration doesn't matter right now. All that matters is that there are 2 ends to each winding, and depending on where you're at in the cycle, one end of the winding can have a potential difference greater than the other, and vice versa. Let's say that for a Y-configured stator, the windings are physically wound in such a way that when A is at a higher voltage than A prime, the A pole is north and the A prime pole is south. When the voltage switches polarity such that A is at a lower potential than A prime, the A pole is south and the A prime pole is north. The same thing could be said for the B and the C coil. Note the arrangement of these 6 poles angularly divide the complete circular stator into 6 equal 60-degree pieces. Real stators, however, feature a bit of overlap between adjacent poles. Additionally, note that traveling in a clockwise direction, A is followed by C prime, which is followed by B, which is followed by A prime, which is followed by C, which is followed by B prime, returning back to A. The purpose of this angular offset and arrangement of particular pole patterns reveals itself when the A, B, and C windings are excited by 3-phase AC that is electrically offset from each other by 120 degrees. The combined effect is a rotating magnetic field on the stator. Any rotor inside this magnetic field would be compelled to follow it in the same direction. Let us first examine each phase's contribution to the pattern at 6 different predetermined times. You'll notice the color code of the poles match the phase. If winding A receives the black L1 phase, at the positive maximum of L1 at time T1, A will be a north pole and A prime will be a south pole. At the negative maximum of L1 at time T4, A will be a south pole and A prime will be a north pole. If winding B receives the red L2 phase, at the positive maximum of L2 at time T3, B will be a north pole and B prime will be a south pole. At the negative maximum of L2 at time T6, B will be a south pole and B prime will be a north pole. If winding C receives the blue L3 phase, at the negative maximum of L2 at time T2, C will be a south pole and C prime will be a north pole. At the positive maximum of L3 at time T5, C will be a north pole and C prime will be a south pole. When these observations are arranged with respect to time from left to right, note that the stator magnetic field will be oriented north to south from A to A prime at T1, C prime to C at T2, B to B prime at T3, A prime to A at T4, B prime to B at T5, C to C prime at T6, and return to the A prime pair. Note that the poles on either side of the pair at maximum intensity are likewise contributing to the effect. If a single pole pair rotor was in this rotating magnetic field, it would be attracted in succession to the A prime pair, the C prime C pair, the B prime pair, the A prime A pair, the C prime pair, the B prime B pair, and return to the A prime pair, having completed one full revolution clockwise for a single cycle of the AC waveform. Even neglecting overlap between adjacent poles, note what this physical and electrical offset is doing. It is dividing the complete stator into smaller portions through which the rotor can be dragged without experiencing unnecessary jerk or lull. The stator, in effect, has become a bucket brigade that smoothly ushers the rotor ever onwards in the clockwise direction. As one pole pair fades out, a fresh, angularly and electrically offset pole pair steps in. But wait, that's not all. Not only does three-phase AC produce a smoothly rotating magnetic field inside a stator, a reversal of the rotational direction is possible with a very cunning trick. Simply by interchanging any two supply leads, the rotational direction of the magnetic field will flip from clockwise to counterclockwise and vice versa. And when I say any, I mean any, as in your choice. I don't care, just randomly grab two and switch them. If you want to go back to your original direction of rotation, just grab two at random and switch them again, even different ones than you switched the first time. You'll find your original direction of rotation returns. This is very important as numerous real-world applications. For example, maybe you want your crane to lower something you may have lifted. You may want to pitch a wind turbine blade into or out of the wind, yaw a wind turbine nacelle clockwise or counterclockwise, or back your electric car into a charging station and then pull out forward. All any of these change of direction tasks require is an interchanging of any two leads. There are those that say that there is a unified industry standard of interchanging line 1 with line 2, but I am here to tell you it is the wild, wild west. Be aware of alternate interchange configurations, but be aware the alternate interchange configurations are accomplishing the same task. For the purposes of this reversal example, let's go with the industry standard and swap L1 and L3. In this case, the A winding is hooked to the blue L3 waveform, the B winding is still hooked to the red L2 waveform, and the C winding is now hooked to the black L1 waveform. As previously, let's first examine each phase's contribution to the pattern at 6 different predetermined times. You'll notice I've switched the color code of the poles to represent this phase swap. If winding C now receives the black L1 phase, at the positive maximum of L1 at time T1, C will be a north pole and C prime will be a south pole. At the negative maximum of L1 at time T4, C will be a south pole and C prime will be a north pole. If winding B still receives the red L2 phase, at the positive maximum of L2 at time T3, B will be a north pole and B prime will be a south pole. At the negative maximum of L2 at time t6, B will be a south pole and B prime will be a north pole. If winding A now receives the blue L3 phase, at the negative maximum of L3 at time t2, A will be a south pole and A prime will be a north pole. At the positive maximum of L3 at time t5, A will be a north pole and A prime will be a south pole. When these observations are arranged with respect to time, note that the stator magnetic field will be oriented north to south from C to C prime at 1, A prime to A at 2, B to B prime at 3, C prime to C at 4, A to A prime at 5, B prime to B at 6, and then return to the C-C prime pair, having completed one full revolution for one cycle of the AC waveform, only this time having traveled counterclockwise. Again, note that the poles on either side of the pair at maximum intensity are likewise contributing to this counterclockwise rotation effect. Any single pole rotor immersed in this stator field would be attracted in succession to the C-C prime pair, the A prime A pair, the B-B prime pair, the C prime C pair, the A-A prime pair, and the B prime B pair, and return to the C-C prime pair, having completed one full revolution counterclockwise. Can you dig it? Simply by interchanging any two leads, we were capable of reversing the direction of the rotating magnetic field. If you need to, by all means, pause the lecture and take some time to let this soak in. If you swap any two phases, even if they're different than the ones we previously swapped, and perform the same analysis, you should see the rotating magnetic field return to the clockwise orientation. Again, this may take some time on your part to visualize, organize, and conceptualize this phenomenon, but the takeaway point is this. By exchanging any two phases of a three-phase AC system, the direction of the rotating magnetic field reverses. If we were to examine the particulars of the rotating magnetic field internal to a two-pole pair per phase stator, we can move beyond our previous simplifications. One could also say that this is a four-pole per phase stator, or, since it's designed to run on three-phase AC, a 12-pole stator. This stator necessitates 6 windings, A1 and A2, B1 and B2, C1 and C2, 2 for each phase. Pole pairs are created from the opposite ends of a single winding wound around an iron core. We'll call the opposite ends of each winding A1 and A1 prime, A2 and A2 prime, B1 and B1 prime, B2 and B2 prime, C1 and C1 prime, and C2 and C2 prime. These windings could be electrically connected in Y or delta configurations, but the electrical configurations don't matter right now. All that matters is that there are 2 ends to each winding, and depending on where you're at in the cycle, one end of the winding can have a potential difference greater than the other, and vice versa. Note the arrangement of these 12 poles angularly divide the complete circular stator to 12 equal 30-degree pieces. Real stators, however, feature a bit of overlap between adjacent poles. Additionally, note that traveling in a clockwise direction, an A is followed by a C prime, which is followed by a B, which is followed by an A prime, which is followed by a C, which is followed by a B prime, returning back to yet another A pole, and the pattern repeats itself. The purpose of this angular offset and arrangement of particular pole patterns reveal itself when the A, B, and C windings are excited by three-phase AC waveforms that are electrically offset from each other by 120 degrees. The combined effect is a rotating magnetic field that the rotor magnet can follow, only this time it will take 2 complete cycles of the AC waveform to complete a single revolution, as we'd expect. If both A windings were excited, such that A's were north and the A primes were south, note that what is created is something called a magnetic quadrupole, where the poles on either side of those receiving maximum intensity likewise contribute to this effect. A magnetic quadrupole is what happens when you take 4 magnets in an alternating arrangement and try to push them into the center of a circle. The 4 magnetic poles interact with the neighbors on either side. The rotor can also be a magnetic quadrupole arrangement. What you get is all 4 poles in the stator interacting with all 4 poles in the rotor, such that norths are attracted to souths and vice versa. Let us now examine each phase's contribution to the pattern at not 6, but rather 12 different predetermined times. You notice the color code of the poles match the applied phase. To fit this all on one screen, note I've got the first 6 times at the top and the next 6 at the bottom. If both A windings receive the black L1 phase, during positive maximums of L1 at times T1 and 7, both A's will be north poles and both A primes will be south poles. During negative maximums of L1 at times T4 and T10, both A's will be south poles and both A primes will be north poles. If both B windings receive the red L2 phase, during positive maximums of L2 at times T3 and T9, both B's will be north poles and both B primes will be south poles. During negative maximums of L2 at times T6 and T12, both B's will be south poles and both B primes will be north poles. If both C windings receive the blue L3 phase, during positive maximums of L3 at times T5 and T11, both C's will be north poles and both C primes will be south poles. During negative maximums of L3 at times T2 and T8, both C's will be south poles and both C primes will be north poles. When we insert the magnetic quadrupole and these observations are arranged with respect to time, note that the stator magnetic field continually revolves in the clockwise direction. However, at time T6, note it has only completed a half a revolution clockwise. The second cycle of the waveform takes it the rest of the way home. Notice because of the quadrupole arrangement, every pole contributed towards angular displacement of the rotor. So my earlier shortcut where one pole pair dominates a portion of rotation is an obvious fallacy, but if you don't care about all the nitnoid details, it essentially yields the same results. The take-home point is for a 2-pole pair per phase stator, the magnetic field does a half turn for a single cycle of an AC waveform and completes a full revolution every 2 cycles. If we were to extend this analysis into a 3-pole pair per phase stator, we'd have to perform a similar 18-step analysis through 3 complete cycles of the AC waveform. Trust me, you do not want to sit through an 18-step analysis of a 3-pole pair per phase stator, as much as I don't want to spend 18 hours drawing it. As awesome as this topic is, there are only so many hours in a day. You should understand that a single cycle of an AC waveform will only see the magnetic field revolve a third of a turn for a single cycle of the AC waveform. It would take 3 cycles in succession to complete a full revolution. If you do, however, want to perform another analysis of this same 2-pole pair per phase stator when the L1 and L3 phase is swapped, such that the A windings receive L3, the B windings still receive L2, and the C windings receive L1, by all means be my guest and do so now. You should find that instead of rotating clockwise, this magnetic field with 2 interchanged connections will rotate in the counterclockwise direction, taking 2 complete cycles of the AC waveform to do so. Before we bring this lecture to a close, let me caution you that reversal of the 3-phase AC stator magnetic field must be performed with the utmost of care. On the power or primary side, motor reversal is accomplished using 2 3-pole contactors. One contactor is designated the forward contactor and respectively connects windings A, B, and C to L1, L2, and L3. When the forward contactor closes, this motor will rotate in the clockwise direction. The other contactor is designated the reverse contactor and respectively connects windings A, B, and C to L3, L2, and L1. When the reverse contactor closes, this motor will rotate in the counterclockwise direction. It should be readily apparent that one should never, ever close both contactors simultaneously, as it would result in the most undesirable of circumstances, notably a phase-to-phase connection. In this case, L1 and L3 run headlong into each other with essentially no resistance between them to keep current at a manageable level. Such an event is associated with an arc flash hotter than the sun and a lab instructor whose anger is hotter than 10,000 suns. Never, ever go phase to phase. This is a life-threatening error. It is for this reason that most motor control circuits incorporate several layers of protection to prevent this most heinous of circumstances from occurring. At a basic level, there exists something known as a mechanical interlock. A mechanical interlock prevents the movement of the opposite contactor when the other is closed. When the forward contactor closes, it inserts a wedge in the path of the reverse contactor, and vice versa. An electrical interlock is a means of preventing the coil of the opposite contactor from being energized when the other is already energized. A push-button interlock is a means of disallowing the input signal from reaching the opposite contactor when the other one is being signaled to close. We'll discuss reversing motor starters and various interlock methods in later lectures. For now, you should be reasonably savvy enough to understand that the purpose of these methods, separately or in combination, is to prevent simultaneous closure of both the forward and reverse contactors. Not only does it not make sense to simultaneously spin a motor clockwise and counterclockwise, it is extremely dangerous to do so. In conclusion, this lecture presented the means three-phase AC uses to establish a rotating magnetic field inside a stator. We defined the term synchronous speed and learned how to calculate it. Additionally, we demonstrated that interchanging any two leads of a three-phase device will change the direction of the rotating magnetic field. Finally, we briefly discussed reversing motor starters and interlock methods designed to prevent phase-to-phase events. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.